So last time I started with elementary functions, that is functions of complex variable, exponential, trigonometric, logarithmic, inverse trigonometric, these functions we want to define. I told you that so far our stock of analytic functions was just polynomials and rational functions, and last time I introduced exponential function of complex variable, that is e to the power z. So today I will revise the definition of exponential function again, and let us today discuss some properties of e to the power z. Remember, now we are defining exponential function of a complex variable. So what we want to do is exponential function. So if z is equal to x plus iy, if z is equal to x plus iy, then e to the power z is defined as e to the power z equal to e raised to x into cos y plus I sin y. Now see the dependence. This complex number is given to us, z is equal to x plus iy. What is its exponential? Its exponential e to the power z is defined like this. So this x is here and this y goes here. And last time we saw why we need to define exponential function like this. Actually, on the basis of our requirements that we stated last time, that is, it should be analytic throughout the plane, and when you substitute z equal to x, it should return us the value e to the power x. On the basis of those requirements, we saw that the function has to be like this. So this is definition of e to the power z. So if you understand this formula, all the properties of e to the power z will follow from that. So you see the formula again. If z is x plus iy, e to the power z is e to the power x cos y plus I sin y. So for example, z is 2 plus 3i. Then what is x? X is 2, y is 3. So substitute. So what will be e to the power z? E to the power x, that is e to the power 2 into cos of 3 sin 3, like that it is. Is 3 radians. So this x goes here, y goes here, okay. So suppose if you want e to the power 1 plus I times pi. So what is this? This is x, this is y. So this will be equal to e to the power x, that is e to the power 1 into cos pi plus I sin pi. This x goes here, y goes here. Now cos pi is what? Minus 1. So it is minus e and sin pi is 0. So it is minus e. Cos pi is minus 1, sin pi is 0. So e to the power 1 plus I pi is equal to minus e. Okay. So you may find out value of e to the power z. So use this formula, this exercise, you can do it later on. Find e to the power I pi by 2 e to the power minus 2 plus 3i 3 pi I, like that. So you just see what is x, what is y, and then put in the formula e to the power z equal to e to the power x into cos y plus I sin y. Try to find out this, maybe you can find later on. Here x is 0, y is pi by 2, x is minus 2, y is 3 pi. Just substitute, that's it. Now, what are properties of e to the power z? Last time we saw properties of the real exponential function. Now you can see these notes. Okay. So this exponential function, all the properties we saw last time. Okay. And now, and then this was how we derived the formula also. And now you see the definition there of e to the power z on your screen in those notes. So this definition is given there on the screen, you can see that. Now let us see one by one the properties of e to the power z. Okay. So properties of e to the power z are: what is the real part of e to the power z? What is the real part of the function e to the power z? It is e to the power x cos y, and imaginary part of e to the power z is e to the power x sin y. Because what was e to the power z? E to the power x cos y plus I times e to the power x sin y. So we know how we write every function fz as uxy plus I times vxy. So this is uxy actually. So for function e to the power z, this is our uxy and this is vxy. Because it is e to the power x cos y plus I times e to the power x sin y. So these are real and imaginary parts of the function. So this is u and this is v. So when we express e to the power z as uxy plus I times vxy, this is actually u. So uxy is e to the power x cos y and vxy is e to the power x sin y. Now the analyticity of e to the power z we can derive from this u and v, because we know what is relation between analyticity of function fz and u and v. So what is our theorem? If u and v are differentiable and they satisfy, yes, and they satisfy Cauchy-Riemann equations, then fz is analytic. So we want to derive that this e to the power z is analytic. For that we are going to show that this u and v are differentiable and satisfy Cauchy-Riemann equations. Now you see this, what is u and what is v. This is u and this is v. Where this e to the power x appearing here is our real exponential function of real variable. E to the power x, exponential function of real variable. And we saw properties of this real exponential function last time. Cos y, sin y, this is y is also real, so this is real trigonometric functions. So we know for last so many years We know these functions, exponential, these are real functions. So this is differentiable. E to the power x cos y is a differentiable function. In fact, first order partial derivatives of these are continuous. So it is continuously differentiable. So let us find out first order partial derivatives of this u and v. So dA by u by dA by x is equal to what? DA by u by dA by x. This is u. So can you find dA by u by dA by x? Yes. It is e to the power x cos y. DA by u by dA by y. This is u. So what is dA by u by dA by y? Partial derivative with respect to y. Minus e to the power x sin y. DA by v by dA by x. What is that? This is v. So dA by v by dA by x is e to the power x sin y. And dA by v by dA by y, this is v. So partial derivative with respect to y is e to the power x cos y. Now you see these four equations and tell me, what do you observe? These four equations. What do you observe? What do we want? So all the four equations. What do we want? dA by u by dA by x we want to be equal to dA by v by dA by y. So what is dA by u by dA by x? E to the power x cos y. What is dA by v by dA by y? E to the power x cos y. So do you see that dA by u by dA by x equal to dA by v by dA by y? Now what is dA by u by dA by y? It is minus e to the power x sin y. And dA by v by dA by x, e to the power x sin y. So dA by u by dA by y is minus dA by v by dA by x. So looking at these four partial derivatives, what can you say? And what are these functions? This is our real exponential, real trigonometric functions which are all infinitely differentiable and so on. So I can say that dA by u by dA by x, dA by u by dA by y, dA by v by dA by x and dA by v by dA by y are continuous throughout R2 and satisfy Cauchy-Riemann equations. Is dA by u by dA by x equal to dA by v by dA by y and dA by u by dA by y is minus dA by v by dA by x. So dA by u by dA by x, dA by u by dA by y, dA by v by dA by x and dA by v by dA by y are all continuous throughout R2 and satisfy Cauchy-Riemann equations. But this exactly means that the corresponding function f, which is u plus iv, must be analytic. So I will repeat the theorem. We have learned in the last chapter that if fz equal to uxy plus I times vxy and u and v have property that the first order partial derivatives are continuous and satisfy Cauchy-Riemann equations, then fz is analytic. Now here Cauchy-Riemann equations are satisfied throughout R2 and these partial derivatives are also continuous throughout R2. So I can say that e to the power z is analytic throughout the complex plane. So just from the definition of e to the power z, we come to know what are u and v, and from u and v we come to know that Cauchy-Riemann equations hold and therefore it is analytic everywhere. Okay. So e to the power z is analytic everywhere, thus is analytic everywhere in C. Everywhere in C. That is, it is the entire function. E to the power z is an entire function. In these notes, this property will come later, but then I wrote u and v, so immediately we could find out the partial derivatives, and therefore we got that partial derivatives are continuous and satisfy Cauchy-Riemann equations, so function is analytic. Okay, next property of e to the power z is mod of e to the power z. Now what is mod of e to the power z? It is e to the power x cos y plus I times e to the power x sin y. So mod of e to the power z is e to the power 2x into cos square y plus e to the power 2x into sin square y and square root. This is u square plus v square square root, that is mod fz. If fz is u plus iv, mod fz is u square plus v square square root. But now this e to the power x 2x, if you take outside, e to the power x will come out and cos square y plus sin square y is 1, and we are taking positive square root. So this will be only e to the power z. Mod of e to the power z is e to the power x. So for example, if you have a mod of e to the power 1 plus 2i, so z is what? 1 plus 2i. So what is x? X is 1. So mod of this is e to the power 1, that is e. Suppose you have e to the power minus 3i. What is mod? Now x is 0. So e to the power 0, that is mod is 1. Absolute value is 1. So mod of e to the power z is e to the power x, where x is what? X is real part of z. Z is x plus iy, remember. So mod of e to the power z is e to the power x. And again from the definition of e to the power z, that is e to the power x cos y plus I times e to the power x sin y. You remember this formula, e to the power z is e to the power x cos y plus I times e to the power x sin y. Take the modulus. So everything will follow from definition. So if you apply definition of modulus, you will get modulus. Now what is argument of e to the power z? Argument of e to the power z, that is y. That is exactly y. Because e to the power z is what? What is e to the power z? Let me write again. It is e to the power x into cos y plus I sin y. So this is exactly polar form of e to the power z. So this is modulus and this is argument. This is argument of e to the power z. So is this clear that this is argument? So modulus of e to the power z is e to the power x and argument of e to the power z is y. So suppose if you have argument of e to the power minus 1 plus 5y, what will be argument? Argument is 5. Suppose if you have argument of e to the power 1 minus I pi by 2. Argument is pi by 2. Argument is y. If z is x plus iy, argument is y. So modulus of e to the power z is e to the power x, and argument of e to the power z is just y. Now next property is that if you put x equal to 0, x equal to 0, okay. So then e to the power iy, so x I am putting 0. So what do I get? E to the power 0 into cos y plus I sin y. That is e to the power iy. This is 1 now. That is cos y plus I sin y. You must have used already this formula in physics, or maybe in FYBSc mathematics complex numbers course. The e to the power I theta is cos theta plus I sin theta. But that is actually a particular case of e to the power z where the real part x is 0. So if x is 0, you get this formula that e to the power iy is cos y plus I sin y. So next property is e to the power 0 is 1. E to the power 0 is 1. Is this obvious? Because z is 0, that is x is 0 and y is 0. So x is 0, y is 0, that means this term will be 0, cos y will be 1, e to the power 0 is 1, so this is 1. And e to the power z is not equal to 0 for any z. E to the power z is not equal to 0. E to the power z is never 0 for all z in C. Why? Simply because mod of e to the power z is e to the power x. Alright. So if e to the power z is 0, then mod of e to the power z, which is e to the power x, is 0, which is not true. Not true. Cannot be true, because we know that our real exponential function can never become 0. Real exponential function can never become 0. So there is no complex number for which e to the power z will become 0. Because if it becomes 0, what is its modulus? Let us find. That is always e to the power x, which we have derived the formula. So it will mean that e to the power x is 0, which is not possible. The next property is, if you read on those notes, in those notes, that e to the power z is on the circle with center at origin. E to the power z is on the circle with center at origin and radius e to the power x, and makes an angle y with the positive real axis. Let us see this property. Okay. So let us now, this is important geometric property, so maybe you can watch what exactly is going on. Remember that when you are dealing with functions of complex variable, The functions are from C to C. So one copy of C and the other copy of C. So this is complex plane and this is complex plane. Now the function I want to think about is e to the power z. So suppose if I take z here, suppose if I take x plus iy, then this is x, this is x and this is y. Then what is e to the power z? E to the power z is e to the power x into cos y plus I sin y. That is our formula. So this point will be mapped to what? It will have absolute value e to the power x. Look at this as if it is in the polar form. So this e to the power z for this z will have absolute value e to the power x. But absolute value e to the power x means what? It will be on the circle with radius e to the power x. So suppose this is circle with radius e to the power x. Radius e to the power x. Because mod z equal to r is a circle with center at 0 and radius r. But mod of e to the power z is e to the power x. So e to the power z will lie on the circle with center at origin and radius e to the power x. And then this angle is y because so this point is e to the power z. That point is e to the power z because this point has modulus e to the power x. Modulus you can also interpret as distance from that point to origin. So this is e to the power x and its argument, that is its angle with positive x axis, is y because argument of e to the power z is y. So therefore e to the power z will be of this type. So z is x plus iy, then e to the power z will lie on circle with center at origin and radius e to the power x and making an angle y. So this x, then e to the power x you can get, and then consider a circle of radius e to the power x. And then this y you take up as the argument. So this y radians angle it has to make with the positive x axis. And then point that you get is e to the power z actually. So you know x and you know y. So consider circle of radius e to the power x and on that circle make an angle y with positive x axis. Then the point that you hit on that circle is e to the power z. So now see the relation between z and e to the power z geometrically. That is, you may start with any z, then you know x. So now consider circle with center at origin and radius e to the power x. Why? Because we know that modulus of e to the power z has to be e to the power x. And now we also know that argument of e to the power z must be y. Therefore this e to the power z is exactly that point which will make an angle y with the positive x axis. So on this circle which point is e to the power z? That will depend on y. So it should make an angle y radians with positive x axis. So this is e to the power z. So suppose if you take this point, okay, then this is your x and now y is negative, okay. So this e to the power z will go somewhere here, because now this is e to the power x. So e to the power x radius will be this circle, suppose, because this is x is smaller than the earlier x, and now makes an angle whatever negative quantity this has. So somewhere here it will come, maybe e to the power. So suppose this point, if I denote z dash, then this is e to the power z dash, like that. So that is how e to the power z goes from C to C. Okay. So this sentence is important, that is e to the power z is on circle with center, origin and radius e to the power x, and making angle y with positive x direction. So that is how you can geometrically describe e to the power z. Okay. That is how you can describe geometrically. That is, you take a point, then you know x and y, and then you draw a circle of radius e to the power x around origin, and then look at y and exactly take that point on the circle which makes angle y with the positive x axis. So that is what e to the power z is geometrically. Let us further analyze this geometry. So let me again draw this picture. Maybe you can see this for a minute. You can see this entire screen for a minute. So from this picture to this picture, from this to this, can you see this? Can you read everything written there? Okay. Now let us further analyze. So I will again draw this complex plane. And again consider this mapping e to the power z. Now let me take a straight line parallel to y-axis. So suppose if I take this straight line. So a line parallel to y-axis is what? Of the form, say, x equal to c. So every point on this straight line has x coordinate c. So that is, x coordinate is constant and y changing. Now if I take a point z here, its x coordinate will be what? X. And y coordinate will be this y. I may change, then y coordinate will change. But what is constant? The x coordinate. Now e to the power z, when you map z to e to the power z, what depends on x? The modulus is e to the power x, remember. Modulus of this is e to the power x. So if I take a circle with center e to the power x, so suppose this is circle with center at origin and radius e to the power x, then this entire line will go on this circle. Is this clear to you? Because for any point on this line, x coordinate is fixed. Okay. Now this x I have taken c, so it is e to the power c. This x coordinate is c throughout this So when you take e to the power z, so this is c plus iy, where this is whatever y. So x coordinate is c throughout, even if you take here it is c plus something, I times y dash, whatever. But x coordinate is c. So e to the power z, modulus will be e to the power x. For all these points, modulus will be e to the power z. So all these points will be on the same circle because they have same modulus. That means they have same distance from origin, and that distance is e to the power c, because modulus of e to the power z is e to the power x. So all complex numbers on this line will have same modulus, that means they will lie on the same circle, and that modulus is e to the power c. So if you read point number 5 now, if you read point number 5, it says that, you see that picture and read point number 5, it says that e to the power z maps a line parallel to y axis, say x equal to c, onto the circle with center at origin and radius e to the power c. Is this clear? That is the entire line, this entire line goes on the circle. So if you take this c plus iy, then this point exactly goes where? Then you have to see what is y. So this is corresponding y coordinate, this is distance y, that much you have to take angle. So suppose this, let me take y1, okay, and let me take this as y2. So this is suppose y1. So this will be what? E to the power c plus I y1. And if this is y2, okay, so maybe this point you may get, say like this. It will be on the same circle, but this angle is suppose y2. Then this is e to the power c plus I times y2. Clear? Exact image point will depend on y, but all these points will be mapped to points on this circle. Now if you take y1 plus 2 pi, what will happen? So suppose if I have this point as c plus I times y1 plus 2 pi, then this point will go on this circle and angle will be y1 plus 2 pi, but this angle is y1. So y1 plus 2 pi you get again same. So same point you get. So this is also e to the power c plus I times y1 plus 2 pi, because the argument is y. So y plus 2 pi, if you take, you will get same point. So long as you have fixed the x coordinate, you will keep getting points on the circle, and if y coordinate differs by multiple of 2 pi, then you get same point actually, because y1 and y1 plus 2 pi on a circle, if the angle y1 and y1 plus 2 pi are same, so they will represent same point. So this is important property which says that e to the power, say z, if you take and then just add a multiple of 2 pi, so c plus I times y plus 2 pi is same as e to the power c plus iy. Have you understood this? You can also directly check by formula which is written here. You can also directly check by the formula which is written here, because y is changing. Y plus 2 pi, if you put here cos of y plus 2 pi is cos y, sin of y plus 2 pi is sin y. So you get same point. So two different points, their exponential is actually same. two different points have same value of the exponential. This is definitely different from real exponential, because real exponential function is 1 1. 1 1 means distinct points are mapped to distinct points, whereas complex exponential is not 1 1. If you change the argument by a multiple of 2 pi, I may take 4 pi now, 6 pi. So in general, I may multiply by n, no problem. I will still get c plus iy, because this angle is y, then this y plus 2 pi, y plus 4 pi will be same angle. And the real part of z is c. So the modulus of e to the power z is e to the power c. That I have fixed. So all these points will be on the circle. So if you look at this line x equal to c and keep taking multiples of 2 pi, so this is z and then y1 is imaginary part, so y1 plus 2 pi. Suppose this is c plus I times y1 minus 2 pi, then also you get same. So if you just keep changing the argument by multiple of 2 pi, you hit the same point there. That is what I have written here. Okay. And importantly, this entire line is wrapped in this fashion around the circle. So the entire straight line is wrapped around the circle. Is this clear? The line parallel to y-axis goes to a circle. Now let us analyze what happens to a line parallel to x-axis. Okay. So before that, you see this picture again. Okay. So this is mapping e to the power z. So you see this picture again now. Now let us go to line parallel to x-axis and see what happens. So shall I draw another picture? Have you finished looking at this picture? Is this clear? That line passing through, line parallel to y-axis goes to a circle. And which circle? The circle is, if this line is x equal to c, then circle has radius e to the power c. And how the points actually are mapped onto the points of the circle, that depends on y. So it keeps making angle y. So this is, suppose this y, then it will be here. And then as y goes, it will move like that and make the angle y with positive x-axis. Now let us consider same type of picture again, but now let us consider lines parallel to x-axis. So let me consider this line now. Okay. Now line parallel to x-axis is of the form what? Y is equal to k, suppose. Our mapping is e to the power z. So I want to take a point on this line now and see where this line goes. So suppose this z if I take, then I know that y coordinate is k. So suppose x coordinate is, so this is x plus I times k. So x plus I times k, this is this point, this particular point. Now this point will go to what? This point will go on a circle of radius e to the power x. Okay. So this will be on the circle of radius e to the power x. So this is e to the power x. Okay. But now this k is fixed. So suppose this is k. So this radius is e to the power x. So we have nothing to do with the other points. We just know that the modulus is e to the power x. Now this, if I take this other point whose coordinates are x dash plus ik, the argument will be same now. So it will be on the same, but this x is smaller than x dash. So e to the power x is smaller than e to the power x dash. So it will be on the same line. Why on the same line? Because k is fixed. K is the argument. So this will be e to the power x dash plus ik. This is e to the power x plus ik. So you will keep getting on the points on this ray. So see again, this point is x plus ik. So e to the power this will have argument k, which is fixed now. So this is fixed now. You will keep getting points on that ray. As x moves, what changes? The absolute value changes. So this distance from the origin changes. So if this is x, e to the power x is difference. If this is your x, you will get point like this. If this is your x, you will get. If you go here, you will get points like this. If you go this side, you will get points near this. So line parallel to x-axis is mapped to a ray. It is written there. Now you read this point 5. It maps a line parallel to x-axis, say y is equal to k. This is line y equal to k, onto the ray emanating from the origin. So this is ray, and making angle k radians with the positive x-axis. This is k radians. Okay. So this is k, the positive x-axis. So this is the geometry of the mapping e to the power z. So suppose simultaneously now if you consider lines parallel to x-axis and y-axis, this point is on the circle of radius whatever x and making angle this y with positive x-axis. So all these points will be lie on the same circle. Okay. But if you vary this, the ray will be same and they will be mapped on that ray. Okay. But the modulus will keep changing. So this modulus will keep changing. These points will get. If you fix x, circle will be fixed. If you fixed y, ray will be fixed. If you fix both, means complex number is fixed, you will hit exactly one point. So this y coordinate is also fixed, x coordinate is also fixed, then you will get a unique point here. That is actually the mapping e to the power z. Okay. So now the next property you can also see geometrically, that is property number 6 written there, or whatever, that numbering is there is some correction in the numbering, but next property is for any w not equal to 0, there exists z in C such that e raised to z is w. That is e raised to z is on to C minus 0. Remember that we have already seen that e raised to z is not equal to 0, never 0. But all other points it takes. That means if you take any point here, any point here, any point here, then you will get a point z such that z is mapped to the given point. That means except for 0, e to the power z takes all the values. So if I start with w in C, okay, and w not equal to 0, then I may write w in the polar form, that is, say suppose r into cos theta plus I sin theta okay. Then I know that w has modulus r, mod w is r, and one of the values of the arguments is theta. So argument w is theta. Now, can I find Z? So, to find Z such that e to the power Z is W. But we know that if there is a Z like this, then e to the power Z has modulus e to the power x. We want to find this Z. This Z is going to be some complex number. So suppose Z is x plus iy, then what is mod of e to the power Z? E to the power x. But mod W, W is given, that is R. So we want for such x, e to the power x equal to R. So we must have then we have e to the power x is equal to R. Okay, we must have e to the power z equal to e to the power x equal to R. So what x I must take? So x I must take as log R. This log is our real logarithmic function because this R is a positive real number. R is nothing but mod W. R is mod W. So R is positive real number. So I can always find x such that e to the power x is R. X is nothing but log R. Okay. So I have found x. Now I want to find y. And then I will take z equal to x plus iy and show that e to the power z is W. W is given complex number. W is given. W I have written like this. Mod W is R. But we know that if z is x plus iy, then mod of e to the power z must be e to the power x. But mod W is R. So I get e to the power x equal to R. Now argument of e to the power z is y. We already know, we have already seen this, that for any z, argument of e to the power z is always y. But e to the power z we want equal to W and argument of W is theta. So theta must be y. Or we have to take y should be equal to theta. So let z equal to x plus iy, that is log R plus I times theta. Then what is e to the power z? Then e to the power z is by definition, this is x plus iy. So e to the power log R plus e to the power x into cos y. This is y. Cos theta plus I sin theta. But e to the power log R is R. So this is R into cos theta plus I sin theta. So that is actually W. E to the power log R, do you see that this is R? But R into cos theta plus I sin theta we took as W. So I get that e to the power z is W. So if W is any non-zero complex number, I can express it in the polar form and from that I can find z such that e to the power z is W. So all the complex numbers, so you look at this picture again. Maybe you can first read this. First read all this. So I have proved that if W is given non-zero complex number, so I can write in the polar form, then mod W is R, argument W is theta. then we want to find z such that e to the power z is w. So I want to find x and y, z means. So I take x as log r and y is equal to theta. If I take that and form x plus iy, that is log r plus I theta, and apply definition of e to the power z, I get this. See geometrically now. So suppose your w is here. Now see the same thing geometrically. Suppose your w is this point. Then what is this distance? This distance is mod w. This distance is mod w. So this is r. So whatever is this distance, I will take logarithm of that. So I will consider x to be log of mod w. So I will take log of this quantity, that I will get x, that I will locate the coordinate x. So where this x is nothing but this. Now I will count this angle with the positive x axis. So suppose this is theta, then I will exactly go theta on this. So this is theta. Okay. So I will take y to be theta. So now this is, so y to be theta. Y, this distance I have taken looking at this, then this point will go to this point under e to the power z. This point will be mapped to the point w. So that is how the mapping goes. Okay. So for any non-zero w, so therefore I have just now proved that for any non-zero w, there exists a complex number z such that e to the power z is equal to w. Remember that exponential function of real variable does not take negative values, but this e to the power z will take negative values also. It takes all complex numbers except for 0. It takes all the complex number. See, for example, e to the power I pi. What will be e to the power I pi? So now x is 0, so e to the power x cos y plus I sin y. But e to the power 0 is 1, so it will be just cos pi plus I sin pi. But what is cos pi? It is minus 1, sin pi is 0. So e to the power I pi is minus 1. So exponential of some quantity is negative. This is different from what happens in the real variable. In real variable, e to the power x is always positive. We know that e to the power x is positive, but e to the power z can take negative values. See this, okay? Mod of e to the power z tends to infinity as x tends to infinity. Next property is mod of e to the power z, which is actually e to the power x. So this goes to infinity as x goes to infinity. Okay. And in fact mod of e to the power z is e to the power x, which goes to 0 as x goes to minus infinity. So on real axis, if you take real part of z to be large negative, then the absolute value of e to the power z is going to 0. So it will be on smaller and smaller circles. As x goes to minus infinity, absolute value goes to 0. Okay. And then e to the power z1 plus z2. Okay. E to the power z1 plus z2. Yes, what do we expect? E to the power z1 plus z2 is e to the power z1 into e to the power z2. So you just write this as x1 plus iy1 and x2 plus iy2. So now just concentrate, I will tell orally, this is x1 plus x2 plus I times y1 plus y2. So on this side, okay, let me write e to the power x1 plus x2 plus cos of y1 plus y2 plus I sin y1 plus y2. Okay. So this is e to the power x1 into e to the power x2. Okay. And then this is nothing but, you know this, that this is cos y1 sin y2, cos y1 cos y2 minus sin y1 sin y2 and so on. So this will come out to be e to the power x1 into cos of y1 plus I sin y1 into cos y2 plus I sin y2. So this will be e to the power x1 into this, that is e to the power z1 into e to the power z2. Multiplication of these two is this actually, because this I square is minus 1, cos y1 cos y2 minus sin y1 sin y2, that is the real part. Cos y1 sin y2 plus sin y1 cos y2 is imaginary part. So e to the power z1 plus z2 is e to the power z1 into e to the power z2. This can be expressed in the group theoretic language. That means this z1 plus z2, that is additive group of complex numbers, and if you consider non-zero complex numbers, it forms a group under multiplication, and then exponential function is a group homomorphism from additive group of complex to multiplicative group of non-zero complex